This video will finish up Chapter 7. We'll start off doing a practice problem on alkene addition, then we'll talk about carbocation structure and stability. Remember, that's an intermediate in these alkene addition reactions. We'll talk about something called the Hammond postulate and how that helps us to determine what a transition state looks like. Then we'll get into carbocation rearrangements. This is a tough subject that students find difficult, so you want to make sure that you have your coffee for this. You may even need to pause the video and come back to it. And then I'm going to finish up with an overview of the 4 types of mechanistic steps. So what if I asked you to figure out the alkene required to prepare the following product? So you know that an alkene plus HX will give you a product where you've gotten rid of the alkene and you've created 2 new bonds, one to a hydrogen and one to a halogen. So the halogen in this case is iodine, so the reactant must have been HI. And we know that the halogen goes on one of the 2 carbons that made up the starting alkene. So if we look at this product, we know that the iodine is on this carbon, so that carbon was in the original alkene. But was that carbon double bonded to this carbon, or this carbon? Well, let's draw out the possibilities and then evaluate it. So that's one possible alkene that we'll evaluate. And another possible alkene would be this alkene that would be formed from a double bond between those carbons. And then the other alkene, that's actually the same compound as the one I drew initially. It's just flipped over. So these carbons, if I drew a double bond to either carbon there, I would get the same starting material. So let me just consider these 2. So when I add HI, the H goes on the carbon with more H's, and the I goes on the carbon with less H's. So if I reacted that alkene, the iodine would go here, and the H would go there, which now does look like the product. So that could have been the starting alkene. But what if I reacted my other possible product? So here, this carbon is the one with more H's, and this carbon has less H's. So the H would go on to that carbon with more H's, and you would end up with this product, which is identical to what I just drew. So what does this tell me? It tells me that either alkene, when reacted with HI, would give me the product that you see here. So sometimes I give you a reactant and then I ask you to draw the product, but I could also give you the product and have you figure out what was the starting material, and it's like a complex puzzle for you to solve. So why don't you try this yourself? So here is the product, and this came from some alkene plus HBr. So pause the video and see if you can figure out what alkene that would have come from and put your answers in the chat. You can either paste an image or you could just write the name of the alkene. So remember, this is the carbon with the halogen attached. So you know that that carbon was double bonded in the starting material. The question really then is just, was it double bonded over here or over here? So you could draw out both of those alkene options and then do the reaction, have it add to HBr, remembering that the H goes on the carbon with more H's and the Br goes on the carbon with less H's. Now the intermediate formed in these alkene additions are carbocations. A carbocation is planar because it's sp2 hybridized. So it has 3 sp2 hybrid orbitals forming these sigma bonds, and then it has an unhybridized p orbital, which is empty, that extends above and below the carbon like this. Now, stability of a carbocation increases with increasing substitution. So a methyl would be the least stable, but as soon as you add one R group, that becomes more stable, 2 R groups even more so, and 3 R groups even more so. There are 2 reasons that highly substituted carbocations are more stable than less substituted ones. The first reason is inductive effects. What does that mean? That means that these alkyl groups attached to the carbocation carbon are inductively sending electron density to that electron deficient carbon. So inductive effects occur through sigma bonds, so it's a shifting of electron density through sigma bonds. And you can see from these electrostatic potential maps that the blue color is not as large as we increase in stability, and the blue relates to positive charge. So over here we have 3 alkyl groups. These 3 methyls are inductively sending electron density toward that positive carbon, which is stabilizing. The second reason is that hyperconjugation, which I introduced last time. So with hyperconjugation, the CH bonds are overlapping with the empty p orbital on the carbocation carbon, and that has a stabilizing effect. Now, carbocations can undergo something called a rearrangement that comes in 2 flavors. We have the 1,2 hydride shift and the 1,2 methide shift, also called a 1,2 methyl shift. So in this, we have a hydrogen moving over with these 2 electrons. And so it's moving over just 1 atom over to the carbocation carbon. When it does that, the positive charge moves to where that hydrogen atom came from. Here we can also do that with a methyl shift. So we can take an entire CH3 group and we move it along with the 2 electrons. So we have a normal headed arrow here. We move it with its 2 electrons to the other carbon, and then the positive charge also moves. So importantly, shifts can only occur from an adjacent carbon, and they will only occur if a more stable carbocation results. So this carbocation is a secondary carbocation. It's secondary because it's attached to 2 other carbons. But when we do the shift, this becomes tertiary, and that's more stable, so that's good. Over here, this carbocation is also secondary. On this adjacent carbon, there aren't any hydrogens to move, but there is a methyl we could move. So we're going to shift over that whole methyl group, and as a result, we get a more stable tertiary carbocation. Whenever you encounter a carbocation, you must consider if a rearrangement, either a hydride or a methyl shift, will result in a more stable carbocation. So for example, what we have here is a secondary carbocation. It's attached to 2 other carbons, which is why it's secondary. And the question is, could it rearrange to a more stable carbocation? If it can, it will. So to determine this, you start by identifying the hydrogen atoms and or the methyl groups on neighboring carbon atoms. So here are the neighboring carbon atoms to that carbocation. And this carbon has 2 H's, the carbon on the right has an H and a methyl. So those are the things that could be shifted if that shift will result in a more stable carbocation. So next you have to determine if shifting one of those groups does result in a more stable carbocation. And it turns out that if you shift this hydrogen with its electrons, you get a tertiary carbocation as a result, which is more stable. If you were to shift that hydrogen, you would get a secondary carbocation, which is no better than what you started with. And if you instead moved the methyl, so if you tried to shift the methyl, you would get this structure, which is also secondary, so that's also no better than what you started with. So we're looking for an improvement in our life circumstances. And going from secondary to secondary, that's a lateral move, That's not an improvement. It's not going to happen. But going from secondary to tertiary, hey, things are looking better. So that will happen. Carbocation rearrangements are generally irreversible. And that's because there's no driving force to go from a more stable compound to a less stable compound. However, there is driving force to go from a less stable to a more stable. Here is an example of a reaction. So if we have 3,3-dimethyl-1-butene and we react it with HCl, first the H goes on the carbon of the alkene with more H's, and that gives us a secondary carbocation. So now we have to stop and ask ourselves, could a hydride or methyl shift occur that would give us a more stable carbocation? And the answer is yes. In this case, here are our neighboring atoms. We could move one of the methyls on the left over and get a tertiary carbocation, which is better. And then in the second step, the chloride attacks the carbocation, and you get this as the major product. You don't see much of that. And hydride shifts aren't only done in the lab, they actually occur spontaneously in biological systems. So this is one small step from the biosynthesis of cholesterol, which involves a hydride shift. Now pause the video and determine if the following carbocations A, B, and C will undergo a rearrangement. If yes, indicate whether it will be a hydride or methyl shift and which neighboring carbon the hydride or methyl shift will be shifted from. Now Dilly wanted me to remind you that in approaching this problem, you should look at the neighboring carbons and determine what hydrogens and methyls they have, and then ask yourself, if you use one of those hydrogens or methyls and perform a shift, will that result in a more stable carbocation? And treatment with HBr vinyl cyclohexane undergoes addition to yield this product. Using curved arrows, propose a mechanism. So pause the video here and try this on your own, and then resume it and I'll go through the solution. So here are reactants. So in the first step, the pi bond will break and attack the H of the HBr, breaking the HBr bond. And remember, Markovnikov's rule says that the H of the HBr will go on the carbon of the starting alkene with more H's. So there's that H, and then the other carbon of the alkene becomes the carbocation. So I'm going to put on the brakes here because I have a carbocation, and I need to ask myself, can a hydride or methyl shift occur to give me a more stable carbocation? This is a secondary carbocation. That carbocation carbon is connected to two other carbons. So I look at my neighbors. My neighbors have H's. There are no methyl groups on my neighbors. So I would just be looking at a hydride shift here. And it does turn out that I could shift this hydride and get to a more stable carbocation. So now I have this carbocation, which is tertiary. So I improved my stability, and now I have a tertiary carbocation. So finally, the bromide is going to come back into play here as a nucleophile. My carbocation is my electrophile in this step, and it's going to add to that carbocation carbon. And there's my product. And now I have a follow-up question. Is this product chiral? Let me know in the chat. Let's move along to look at energy diagrams. So in our energy diagrams, we have starting materials over here and products here. So this would be an example of a spontaneous exergonic reaction because the products are lower in energy than the reactants. So that would be the delta G of the reaction. The hills are called the transition states, and the valleys are the intermediates. So the number of transition states corresponds to the number of steps. So 1, 2, 3. There are 3 transition states, which means this reaction has 3 steps. A transition state is the high energy state a reaction passes through. They are fleeting and they cannot be observed. And bonds are breaking and forming in the transition state. And in chemistry, we represent breaking and forming of bonds with these dashed bonds. Now, how do we know what that transition state looks like? Because I just said it's fleeting and it can't be observed. Well, the Hammond postulate says that 2 points on an energy diagram that are close in energy should be similar in structure. And based on this assumption, we can generalize the structure of a transition state depending upon whether the reaction, and in particular the reaction step we're looking at, is exergonic or endergonic. Now, every time you see the word exergonic, you may think exorcist. And actually, those 2 words are related through the EX at the beginning of the word. So in this clip, this shows an exorcist casting out the demon from a young girl from that old movie, The Exorcist. And EX just means to release or to come out of. And so similarly, in an exergonic reaction, energy is being released, just like an exorcist is trying to cast out a demon from a possessed person. And then endergonic means energy is being absorbed, or things are going into something else, not coming out of something. So in an exergonic reaction step, the transition states resemble the reactants because they're closer in energy. In an endergonic reaction step, the transition state resembles the product because those are closer in energy. So the figure in A shows the typical reaction that we see. And that is where, if you have 2 competing pathways, the faster pathway leads to the more stable intermediate. And you know this is faster because it has a lower hill, it has a lower activation energy. And the slower reaction, on the other hand, would lead to the less stable intermediate. So that's the energy diagram that most corresponds to the reactions we'll see. So in this case, we think about the high road and the low road. So while in our personal lives, it's always good to take the high road, in thermodynamics, we always take the low road. So we're going to go over the lowest hill. That's going to be the fastest way to get where we want to go. Now, this reaction does describe the alkene additions that we've been discussing. There is a possibility that you could get something like this, where actually the faster reaction leads to the less stable intermediate, but this is much less common. So let's look at this in the context of the alkene addition. So in the alkene addition, we form a carbocation by protonation of an alkene, and that's an endergonic step. Thus, this transition state will structurally resemble the carbocation intermediate, because this is closer in energy to the transition state than the starting material. Therefore, any factor that stabilizes the carbocation will also stabilize the nearby transition state. Since increasing alkyl substitution stabilizes carbocations, it also stabilizes the transition state leading to those ions, thus resulting in a lower hill and a lower activation energy and a faster reaction. In other words, more stable carbocations form faster because their greater stability is reflected in the lower energy transition state leading to them. The final topic I want to mention is on mechanisms and arrow pushing. So we've talked about this a bit and how curved arrows are used to show how electrons move. And there are 4 main ways that electrons move: nucleophilic attack, loss of a leaving group, which we haven't seen and we'll see in later chapters, proton transfers, we have seen that with our acid-base reactions, and then the one I just introduced in this video, rearrangements. So a nucleophilic attack, the nucleophile attacks an electrophile, and the tail of the arrow starts on the electrons of the nucleophile and ends at the electrophilic site of the electrophile. And these electrons end up being shared as a bond. The second pattern is a loss of a leaving group. And we haven't yet discussed leaving groups. We will in the future. But essentially in this, a group leaves a molecule with its electrons. So here the bromide is leaving. It's saying, hey, I'm out of here and I'm taking my electrons with me. And as a result, it leaves and you leave behind a positive charge. This is a more complicated example of kicking off a leaving group involving a series of electron pushes and arrows. The third type is a proton transfer. So whenever we're shuffling H atoms around, that's a proton transfer. And here we see the carbonyl compound acting as a base, and it's grabbing an H and it's forming this protonated carbonyl. Here water is acting as the base and it's grabbing a hydrogen and removing it from the protonated carbonyl. Then finally, there are rearrangements, which we just talked about. We will be getting into more and more complex reactions that involve multiple steps, and those steps often will involve one or more of the four patterns that I've covered so far. So this would be an example where in the first step we have a proton transfer, in the second step we have loss of a leaving group, followed by carbocation rearrangement, followed by nucleophilic attack. And then sometimes two of the patterns can occur in a single mechanistic step. So here we have a nucleophile attacking and loss of a leaving group. Now pause the video and see if you can answer the next three questions. I want you to identify the mechanistic steps in the order that they're shown, and your choices are from A, B, C, and D. So this would be step 1, step 2, and step 3. Again, pause the video and look at these reactions and see if you can identify the mechanistic steps in them. And put your answers in the chat.